Alright, let's take a look at some diazotization processes. And what we're looking at here is a nucleophilic process. Up to now we've been looking at electrophilic processes, that is positively charged things attacking the aromatic ring. But it's also possible for negatively charged things to attack the aromatic ring as well. So if we have some sort of species X minus, and the X minus can be delivered via any of these kinds of compounds here, you'll notice that we have metals connected to X. We have where X is Cn, Cl, Br, so that makes them Cn minus, Cl minus, Br minus. We have a metalloid here connected to fluorine, which makes that an F minus. We've got water, which is going to be a source of OH minus. We've got H3PO2, or hydrogen phosphide, which is a source of H minus. And we've got Ki, which is going to be a source of I minus. Alright, so each of these will deliver a nucleophile, or a negatively charged species, that will react with the diazonium salt. The diazonium salt itself is made by taking aniline, which has the NH2, treating it with sodium nitrite, that's sodium nitrite, not nitrate, and HCl, that's NaNO2 and HCl at 0 degrees Celsius. That gives us our diazonium salt. Now what makes these so reactive to nucleophiles is that when the diazonium salt is attacked, it releases nitrogen gas, which is an incredibly stable leaving group, as a product. And of course the nitrogen gas just bubbles off, and there's no way that the reaction can reverse after the nitrogen has gone. So it is an incredibly versatile way to add different things to an aromatic ring. Alright, let's take a closer look at the mechanism and at the X minus groups that I was just talking about. So here's our X minus group, Cn minus, Cl minus, Br minus. They each come from CuX. HbF4 produces F minus, H2O produces OH minus, H3PO2 produces H minus, and Ki produces I minus. And each of these ends up substituting for the N2 plus that we end up attaching to the ring via the diazotization process. I want to take a closer look at the mechanism here. So let's say we've got our N2 plus formed. It looks like this, and sometimes you'll see the Cl negative expressed as a counter ion. It's a spectator. It doesn't really play a part in any of the reactions, so we don't tend to worry about it too much. And let's say we have some kind of X minus coming in. So what happens is the X minus comes in and it attacks the same carbon as the N2 plus is attached to. And then what happens is the electrons in the double bond jump onto the adjacent carbon atom. So we end up getting a C negative at that point. Alright, so we've got our X group attached now, and now we have a negative charge on this carbon atom. Now what happens, in order for the ring to retain its aromaticity, it will reform the double bond and then kick out this very stable leaving group, which is indeed nitrogen gas. Alright, so the leaving group here is very stable N2 gas. And as I said before, the N2 gas simply evaporates or just bubbles off the reaction, and it never has a chance to reverse the reaction and go back to what it was. So that's what makes this such a useful process. It will happen at 0 degrees as well, and then it will you can warm it up to room temperature just to complete the reaction after you've added the X minus at 0 degrees Celsius, and the reaction pretty much occurs straight away, and then you end up getting your product.